if we're given a formula for a function, a really important thing to be able to do is to determine the domain. So remember what the convention is. The convention is the domain is all possible inputs such that the formula makes sense. Simple example, if I took the square root, so radical symbol x, that makes sense as long as x is greater than or equal to 0, because I can take square roots of non-negative numbers, but I can't do it for negative numbers. So radical x, square root x, makes sense as long as x is greater than or equal to 0. That means, by convention, the domain is all non-negative numbers. So the interval from 0 inclusive onwards in the positive direction. Now, calculating domains for more complicated expressions is certainly pretty tricky, right? It's one of these things that requires, well, really two things I think are really necessary. So the key skills to be able to do this are the following, I think, if I had to boil it down. So the key skills, I would say, are, first of all, you absolutely must know the domains of your core function classes, things like power functions, polynomials, rational functions to some extent. In fact, no, definitely rational functions, because they're not too difficult to determine domains of. Exponential functions, logarithmic functions, trigonometric functions, and inverse trig functions. So it's crucial you know domains, and to a reasonable degree ranges of those. So no domain, domains and ranges of your core functions. So that's basically the list I've just reeled off. So that's super important, right? You need to know certainly the domains, and as we're going to see, the ranges to some extent, at least in simple cases. The next thing I think that is a really big issue is understanding how domains are affected by composition. So this is something I think that is very difficult for most people. I certainly found it very hard when I first did this, because it requires really kind of slow, like systematic thinking about things. So understand how composition affects domains. So I think to boil stuff down to the simplest possible things you need to be able to do, it's these core skills that are absolutely vital for determining domains of potentially quite complicated expressions. So what I'm going to do is talk, first of all, in general about how domains work for composites, compositions of functions, and then I'm going to go through examples. And I'm going to go through examples which kind of highlight lots of important things that can happen, things that are likely to turn up in kind of the first few weeks of your calculus classes and things like Math 1A perhaps, or 16A. And then I'm going to build up to a really, really difficult example which basically hits absolutely everything, is very hard, but it's the kind of example that really tests your understanding, your true understanding of not just the question of finding domains, but of our real understanding of lots of our core function classes. Okay, so first of all, let's ask a question. So the question is, when is x in the domain of a composite? When is x in the domain of f composed with g? That's a nice question. So remember what f composed with g is. It's the new function where I, first of all, feed x into g to get gx in output, and then I take that and I replace that, well, I feed that into f. So that output becomes an input into the other function f. So visually speaking, what we have is the following. So we've seen these kind of pictures quite a few times now, but they're really good to see again. So visually, we start off with x, and then I'm going to apply g. Okay, so that gives me what? That gives me gx. And then what am I going to do? I'm going to apply f, of course. That's the meaning of the composite. So this would be gx fed into f, and if we're going to use our standard notation, this is f composed with gx. This picture is going to tell us everything we need to know. What's going to happen for this to make sense? Well, two things have to happen. First of all, we're going to need to have x in the domain of g, right? This needs to make sense. And next, gx has got to be able to be fed into f. So I need two things to happen. I need x to be in the domain of g, and I think I need gx to be in the domain of f. So this picture tells me the following. X is in the domain of the composite if and only if two things happen. So the first thing is x in the domain of g. So that's the first arrow, needs to make sense. And this is very important, and I think this is where things get more complicated or more confusing certainly, we need gx to be in the domain of f. Those two things have to happen. So I think this is sufficiently important, it should be highlighted. So what do we need to understand the domain of a composite? I think we need to know three things really. So we're going to need, so we need to know of course the domain of G. We'll need to understand the domain of G. That's of course obvious. We'll need to understand, well, we're going to have to understand to some extent the range of G as well, because Gx, this thing, is in the range. Remember, it's an output. So we've got to understand not just the domain of G, but the range of G. And then, of course, we've also got to understand the domain of F. So those three things need to be kind of under my belt if I'm doing this problem. So I think this is inherently going to be difficult, right? Because even if we know the domain of G, the domain of F, maybe they're completely core function classes, you've still got to worry about this business about Gx jumping outside the range of F. Right? So maybe it's all fine. Maybe this guy makes sense, this makes sense, but then Gx, for whatever reason, is not in the domain of F, and then you can't go any further. So we're going to have to really understand the output of G in order to solve problems like this, I think, and it's what's going to make things really difficult. So let's boil this down to a strategy, shall we? So here is our strategy to determine the domain of a composite. So I think there are three things that have to happen, and I think we're going to do them in this order. So find the domain of F. Let's do this one first. That's quite a good idea. So I'm kind of going to work from the outside in, if you want. Find the domain of F first. That's going to give me some sense for what the possible inputs are going to be. Of course, we need to know the domain of G, because that gets the ball rolling in the first place. Rolling. And then the most tricky part of all, we're going to have to find all X in the domain of G. such that g of x is in the domain of f. So without any doubt, this third part is the challenging part. This is the hard part. So this is the challenging part. Because that requires properly understanding not just the domain of g and the domain of f, which are very important, but we've got to understand how the function g works. We've got to understand what parts of the range live where and all that kind of thing. So let's do an example. I'm going to jump in with one which is a classic, the kind of one that certainly I have set on midterm exams, first midterm exams. Let's try the following. So let's keep these up here actually a second. So example. Alright, so we want to know the domain of the following function. So let's take the square root, positive square root of course, square root of the quadratic x squared minus 5x plus 6. So we're taking the square root of the entire quadratic expression. Now first of all, and I think again this is a difficult thing about this, we ourselves need to make a choice of f and g. We've got to look at this and be like, okay, is this a composite of reasonable simple functions? I've got to single them out myself. So again, this is something that's difficult about this. So I think this one is really pre-built to fall into this composite pattern. You see, if I was to set f of x to be equal to the positive square root of x, and let's have gx is equal to x squared minus 5x plus 6, well then very clearly the composite is this function. I've kind of come up with the most simple possible way of breaking this up into a composite. And the reason I've done this is, well, first of all, I've just studied composite functions, domains of composite functions, it looks logical. This thing isn't directly one of my core examples, right? Because it's like a polynomial, but at the same time I've got a square root in there, so it's not. But it is a composite of two of my core examples, namely a polynomial and a power function. So let's go through 1, 2, and 3 super carefully here. First of all, 1. So what's 1? It's the domain of f. So this is one of my core examples. One of my core examples, this domain is all non-negative numbers. So this is exactly why it's so vital to have your core classes just at your fingertips. Okay. Next. Domain of G. The domain of G is equal to what? The domain of G is equal to, well, it's a polynomial, so it's everything. Nice and simple. So 3, let me kind of keep this zoomed out a bit. What do we need to do for 3? So here is the tough part. So we need to find, all x in the domain of G, so that's minus infinity to infinity. So I'm just writing out 3 word for word almost, such that gx is in the domain of f, so such that x squared minus 5x plus 6 is in the domain of f. So that's me writing 3 basically word for word in this specific case. Now, this looks like a hell of a convoluted way to describe this, right? We need to find all x in that. Well, that's all real numbers such that this is true. This is actually a really simple statement, right? I mean, let's take a moment to think about what it's actually saying. So x squared, so there's no conditions on x, right? Not really. We don't need to worry about the domain of G. but x squared minus 5x plus 6 is in this interval, well, it's obvious if and only if x squared minus 5x plus 6 is greater than or equal to 0. Okay? So the condition I'm looking for is finding what values of x that expression is greater than or equal to 0 for. And this is kind of obvious from the get-go, I think, right? You look at this up here and you say to yourself, okay, I'm taking the square root of something. I can't take the square root of any negative numbers, so whatever that thing is has to be greater than or equal to 0. So we've gone through a pretty convoluted path to that, but I think it's important you take the time to understand kind of the general pattern so that when we're dealing with more complicated things, you can do it. So I think a lot of you probably see this would be like, you would immediately jump to the statement, okay, we need to have x squared minus 5x plus 6 has to be bigger than or equal to 0. Brilliant. That's fine, but the moment I start to give you, as I said, more complicated expressions, if you haven't internalized these 3 steps, you're going to find it very difficult to do that. So this is the reason I'm being so ridiculously methodical about it. So the moment we have this, we can see we have a very standard problem in front of us. We need to work out when a function is positive, right? So this is going to be a situation where we have to do sign analysis. So must do sign analysis. Must do sign analysis. So to do sign analysis, here, it's a quadratic, there's quite a few approaches, but let's take the most simple. If I can factor this into linears, life is going to be very simple for me. I've got my usual procedure. So thankfully, this can be factored into linears very simply. So x squared minus 5x plus 6 factors as x minus 2, x minus 3. Okay, so generally speaking, what do I have to do when I do sign analysis? Well, I factor it into the simplest possible pieces. Linears are perfect because they're so easy to determine if they're positive or negative. And then I look at each piece in the factoring and I say, well, where is it 0 or where is it undefined? So here these factors are linear. They've got no issues with undefined terms or anything like that. So this guy, we just need to worry about zeros. So both factors are defined everywhere. Defined everywhere, nothing weird going on. So we only need to worry about zeros. That's the only thing we need to look for in my sign analysis. Remember when you're doing this kind of in general, you could have things like denominators, that kind of thing, becoming 0, so then you have undefined positions. That's not really happening here. Okay, so let's just work out where I'm equal to 0. So I'm just going to go through sign analysis now, really carefully. So the first term, x minus 2 is equal to 0, if and only if, of course, add 2 to both sides. X is equal to 2. X minus 3 is equal to 0, of course, if and only if x is equal to 3. Okay, so what does that mean? Well, I'm going to draw a number line. So I'm going to go through my sign analysis procedure. And I'm going to mark on this number line the positions where I could potentially change sign, essentially. And there are 2 locations of interest, 2 and 3. So then what should I do? Well, I need to basically determine if I'm positive or negative between these intervals, between these positions and around them. To do that, I'm going to look at the individual factors. So down here, let's write my 2 factors. Let's do x minus 2 and x minus 3. Okay, x minus 2 is negative before 2, and then it becomes positive afterwards. So positive, positive. This is me marking the sign of that piece. X minus 3 is negative here. It's negative here until it becomes positive here. So then at the top, if I'm interested in the sign of x minus 2 times x minus 3, well, this now is determined entirely by the sign of these 2 factors. 2 negatives multiplied together makes a positive, so I'm positive here. A negative and a positive makes a negative, so negative there. and 2 positives, of course, is positive. That's me doing basic sign analysis. So as always, just here to remind you what we're doing, if I had more factors, I would just be thinking about the number of negative terms in each column. So there's an even number of negative terms here. That's why it's positive on top. And here there's an odd number. And I suppose the last column is even again because 0 is an even number. Alright, so this tells us where we are greater than 0 or less than 0. We do need to worry about being equal to 0 though. Remember, this is the condition we're looking for. And thankfully that's basically obvious. It could only happen at one of these 2 locations, and it happens at both of them. So at these 2 points, we are 0. So these are the zeros of my expression x minus 2 times x minus 3. Neat. So putting all this together gives me the following. So x squared minus 5x plus 6 is greater than or equal to 0. It's badly written, isn't it? It's greater than or equal to 0 if and only if, okay, you're in one of 2 basic locations. So x is in either minus infinity to 2 inclusive of 2, because you could be 0 at 2, or you're in 3 onwards in the positive direction. So that would mean you're in the union of this from 3 onwards. Okay. So let's put everything in a conclusion, right? We've got so much going on. So conclusion. Conclusion. X is in the domain of my original expression. So the square root, what are we? X squared minus 5x plus 6, if and only if. So let's really write this carefully. So x is in minus infinity to infinity, that's the domain of g, the inner function, and x squared minus 5x plus 6 is in the domain of the outer function, that's just 0 to infinity. So this is me writing down step 3 again, right? So this is the domain of the inner function. And this is the domain of the outer function, which is the square root function. But now we've concluded, well, this property is just the statement that x squared minus 5x plus 6 is greater than or equal to 0. We know exactly when that happens now. This is if and only if x is in this union of 2 intervals we just described. So what's the deal? We've got the domain. We've worked out exactly the values of x such that the expression makes sense. So this is the domain of my original function. Right, let's zoom out a bit just to see the whole thing. So this is an awful lot of work. But this is how to do it really properly. And as I said, I mean, for this one, we could probably have like cut short some of it, right? I mean, jumping straight to this stage is not unreasonable, right? Because you can just immediately see we can't take a square root of a negative. But as I said, it's important you can write it out this carefully, because the moment you start to get more complicated things, for example, things like composites of 3 functions, you're going to have to be super duper careful about what can go wrong. Sign analysis, again, is something very important here. It's something that turns up all the time when doing these types of things. Now, there's a warning here as well. This, again, is a classic midterm question because there's a trap in it. And the trap is the following. And I've said this a lot throughout this course, but you don't want to blindly do algebra without thinking about what you're doing. And this actually is a supreme example of this. So, warning. So, it's extremely tempting to do the following. So, what have we got? We've got your function here. You've got your function there. And this, of course, is equal to the square root. It's equal to the square root of the product of 2 things, yeah? So x minus 2, x minus 3, yeah? So it's incredibly tempting to invoke a law of algebra. So a law of algebra, as an example that would be important, would be, well, square root of a times b is equal to the square root of a. This is one of your, maybe it's a law of exponents, would be a better way to put it. It's incredibly tempting to invoke this property, isn't it? Right? The moment you've got a product, it's nice. Completely doesn't make sense for sums, but if I've got a product, it does. But you must understand, this only works under very specific circumstances. And the specific circumstances are a and b must be positive. Or, sorry, non-negative. If either a or b is negative, the right-hand side is not going to make sense. So if you want to sit here and go like, okay, I'm going to simplify this immediately. So if you did that, you would write down the following, wouldn't you? You'd write so you do this, you'd be like dun 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 dun. So I'm just so used to doing this piece of algebra, I'm not even going to think about what it means. So then I would just say, well, all I've got to do now is just do this, and for that to make sense, I would need x plus 2 to be positive, x minus 3 to be positive. I could work that out. That seems easier than having to tangle with this nasty sign analysis. The problem is these are not the same function, and it's exactly the issue we have above, right? So this first expression and the second are not the same. Are not the same function. They would give the same output, sure, if x plus 2 and x plus 3 are positive. But if either of those is negative, one of them doesn't even make any sense. So the issue is they don't have the same domain. They have different domains. So this piece of algebra that we want to invoke only makes sense if x minus 2 and x minus 3 are positive. The thing is that, I'll put this down here. The thing is that in this case, here, you've only got one option, right? That has to be positive and that has to be positive. Whereas over here, sure, it could be positive and positive, but you could also have the situation where it's negative and negative. You see, that's totally fine because it's happening inside the square root. Minus times a minus becomes a plus, then I take a square root. So in the second case, we are losing a whole branch of the domain. So these two are not the same function. So here the domain is, it's, what is it, minus infinity. I've just written it down. Minus infinity to 2, union 3 to infinity, right? It's that. And this corresponds to, this is the minus minus part, and this is the plus plus part. So the second guy has lost the minus minus part. It's devilishly subtle. So this guy, the domain is only 3, so that should be a square bracket, sorry. Improve that a little bit. Sorry, it shouldn't be a square bracket. It should be there. It's only that, right? Because that's the plus plus. If we go up to here, it's this, right? So plus plus. So if you do the following, if you take this and invoke this law of exponents down here, right? And you don't remember that it only makes sense if your a and b are greater than or equal to 0, then you've chopped off the legs of the problem, basically, right? Because you are changing the function. The function is not the same function because it has a strictly larger domain. It has the possibility on the left of minus minus, whereas on the right it doesn't, because you cannot take square roots of negatives, not in the world of real numbers. So, very subtle point, but really important, right? I've on many occasions set basically this question, or a question like this, in a first midterm exam, and it really highlights sloppy thinking, right? If you just automatically say, oh, we'll do this piece of algebra and we're done. All right, no, you've got to be incredibly careful. So this is a difficult example. That's why I'm showing it to you.